the edge of the universe space, the final frontier, a realm of infinite possibilities and mysteries that have puzzled humanity for eons. From the vast voids that punctuate the cosmos to the very beginning of time itself, join us on a journey as we explore the enigmas of the universe and ponder its future. We'll travel back to the dawn of the universe, witness its evolution, and gaze into the distant future. We'll seek the boundaries of the cosmos and question if there truly is an edge to all we know. In the vast expanse of the universe lies a deep mystery that eludes our understanding, a mystery that stirs our imagination and challenges our comprehension. It is the question of what lies beyond the universe. As we travel through space, we're faced with the realization that our vision is limited, imprisoned within the confines of our observable universe. What lies beyond these boundaries remains a mystery, a cosmic curtain that envelops the secrets of existence. The very concept of beyond becomes a philosophical problem. How can we comprehend a realm that lies outside our perception? This challenge pushes the boundaries of human thought, sparking curiosity and encouraging us to seek answers. Everything we see, from the interior of a room to the most distant galaxies observable through massive telescopes, is part of the observable universe. Currently, the radius of the visible universe is 46.5 billion light-years. However, the age of the universe is only 13.8 billion years. How do we explain this discrepancy? It all comes down to the expansion of the universe. Due to this expansion, the regions from which light is emitted are moving away from us, making them appear at a greater distance. These 46.5 billion light-years define the boundary of our observable universe, even if the entire universe itself is infinite. Modern cosmology does not yet know what may lie beyond this observed boundary. These cosmological limits, or horizons, are dictated by light itself. We don't see a night sky completely filled with stars because of the constraints imposed by light. For example, light has a maximum distance from which it can reach observers on Earth, creating a spherical barrier beyond which billions of other distant stars and galaxies exist. This is known as the particle horizon and the event horizon. However, these two concepts differ. While the particle horizon marks the distance from which past light reaches us now, the event horizon defines the distance from the present to an observer in the future. Beyond these horizons lies yet another limit, the Hubble horizon. If celestial objects exist beyond this boundary, it becomes impossible to see them, even after billions of years, as they move away at the speed of light. Because of this, it appears that the universe is limited, though in reality, it is only our ability to observe light that is constrained. Light from bright, cosmic objects does not travel instantaneously. For example, the Sun is located 94 million miles from Earth, meaning sunlight takes about 8 minutes to reach us. Similarly, Proxima Centauri, the closest star to our solar system, is 4.2 light-years away, meaning its light takes 4.2 years to reach Earth. This means that when we look up at the night sky, we are essentially looking back in time. If we wanted to update our knowledge of an extremely distant object, such as the HD-1 galaxy, located 13.4 billion light-years away, we would need to wait that same amount of time, provided there are no obstacles, like black holes, obstructing the light's path. By studying light from the distant past, we have been able to understand the formation of our own galaxy and the evolution of the universe. This principle led to the development of the Big Bang theory, The consequences of the Big Bang left behind traces, one of which was discovered by researchers in the 20th century. Astronomers Penzias and Wilson detected a strange signal with their radio telescopes. Cosmic microwave background radiation, CMB, the remnant of the first light that appeared in the universe. During the early stages of the Big Bang, atoms could not form, and free electrons and protons prevented light from traveling far, making the universe resemble a dense fog. However, after 380,000 years, the universe cooled, allowing the first stable atoms to form. This transition made the cosmos transparent, enabling light to travel freely across vast distances. This light, with a temperature just above absolute zero, minus 454 degrees Fahrenheit, is recorded as microwave radiation, observable in all directions from Earth at a distance of 13.8 billion light-years. This discovery led scientists to estimate the universe's age as 13.8 billion years, although this may only represent the limits of our vision. The cosmic microwave background radiation is not visible to the human eye, as its intensity has diminished over time due to the expansion of the universe. This expansion stretches light waves, reducing their energy and shifting them into the microwave spectrum. Despite its low power, the Large Hadron Collider, LHC, allows us to peer into the origins of the universe. Thanks to the LHC, scientists now understand the Big Bang scenario, tracing the evolution of the cosmos from its singularity to the present moment. In addition to light, other phenomena help us explore the universe beyond our visible range. Neutrinos, tiny fundamental particles with nearly zero mass, are one such example. Because they interact very weakly with matter, neutrinos can travel vast distances at nearly the speed of light. Since they are formed during nuclear reactions in stars, supernova explosions, and other cosmic events, neutrinos can carry information about these processes across hundreds of billions of light-years. Similarly, gravitational waves, ripples in space-time caused by massive cosmic events, serve as another tool for probing beyond our observational limits. Yet despite our efforts to uncover the secrets of the cosmos, we remain constrained by a major factor: the expansion of the universe. Since the Big Bang, this expansion has continued, albeit at a slower rate. However, dark energy is now accelerating this process, causing galaxies and other cosmic objects to move away from each other at increasing speeds. This expansion affects cosmic horizons, including the event horizon, which defines the distance beyond which no signals, including light, can ever reach us. As a result, the universe is gradually becoming less accessible to us. Some galaxies within our particle horizon today may one day move beyond our event horizon, making them forever unreachable. In the far future, even the galaxies with which we can currently communicate may disappear from our reach. The expansion of space is shaping the size of these horizons. Once 60 billion light-years, the event horizon now stands at 16 billion light-years. Over time, this distance will shrink further, isolating us within a cosmic bubble, unable to reach beyond our own limited sector of the universe. Despite humanity's curiosity, the universe imposes boundaries to preserve its infinite secrets. We are surrounded by spherical horizons that limit our ability to study the cosmos. In billions of years, these horizons will merge, blocking all light from beyond Earth, and effectively cutting off our ability to understand the greater universe. However, advances in technology, such as neutrino detection and gravitational wave research, will allow us to gather more data about deep space. Although we may never eliminate these cosmic limitations, we can learn to navigate and manage them. Since the dawn of humanity, we have gazed up at the stars, mapping constellations and dreaming about what lies beyond our tiny corner of existence. But have we ever dared to consider the end, not just of our civilization, but of the universe itself? What will the last moments of the cosmos look like? Will everything end with a bang, or will the conclusion be something completely unforeseen? Throughout history, humanity has thrived by pushing the boundaries of understanding. Today, we embark on the deepest journey yet, a journey to the very end of time. Like grains of sand in an hourglass, each moment brings us closer to the inevitable conclusion of the universe. But how and when will this happen? And what will it mean for us, mere mortals, as we cross unimaginable scales of space and time, and ushered in a new geological epoch, the Anthropocene? This is a chapter of Earth's history written by human hands. As we stand on the threshold of this new era, one question arises. What legacy will we leave to succeeding eras? Our journey brings us closer to the year 2500, revealing the dynamic changes the Earth would face. Earth's magnetic field, our protective shield against solar winds, is undergoing a belated shift. The North and South poles are reversing places, an event last observed 780,000 years ago. This amazing turn is disrupting our technology, forcing us to adapt in ways never before experienced. Let us be transported to the year 4385. We're witnessing the return of an old friend, Comet Hale-Bopp. It is a sight to behold, a bright trail of light illuminating the night sky, a vivid reminder of our place in the universe. Jumping to the year 5000, we're confronted with the grim reality of our past actions. The polar caps have melted, leading to a global sea level rise. Many coastal towns, once full of life, now lie underwater, relics of days long past. In the year 6000, a colossal asteroid looms on the horizon. Its collision with Earth is inevitable, causing a catastrophic event that will change life as we know it. The year 8000, we're witnessing an extraordinary celestial event. A distant star, having reached the end of its life, explodes in a spectacular supernova. Its glow outshines entire galaxies, a reminder of the ever-changing landscape of the universe. The Earth and its cosmos, perpetually in motion, remind us of the impermanence of our journey. As we look at the star-studded canvas of the universe, we reflect on the trials and tribulations that lie ahead on our journey to the end of time. The hands of the clock move forward, 1 billion years. Our sun, the source of all life, begins to change dramatically. Its luminosity increases by 10%, scorching the Earth with unquenchable heat. As temperatures rise, photosynthesis ceases. By 1.1 billion years, the green carpet that once covered the Earth begins to fade, replaced by barren landscapes devoid of life. The air becomes thin, and the oxygen we need is depleted. The relentless heat is accelerating. By 1.3 billion years, the Earth's once vast oceans are beginning to evaporate. What was once a blue pearl in the cosmos is gradually becoming a dried-up brown. The great seas and oceans turn into mere memories. Our journey brings us to the last chapter of Earth's history. In the 7.5 billionth year, the Sun, transformed into a red giant, consumes our once lush planet, marking the end of Earth's existence. Our homeworld, which has nourished us for billions of years, is now returning to the cosmic dust from which it was born. Fast forward to the year 10 billion. After its fiery death, our sun is reborn as a white dwarf, a weak, cooling remnant of its former self. From the raging hell of nuclear fusion, it's now just smouldering embers, a silent spectator to the grand cosmic drama that continues to unfold. By 100 trillion years, there's a deep silence over the cosmos. The stars, beacons of the universe, begin to go out one by one. They leave behind a chilling darkness, a universe in twilight. By 1 quadrillion years after the extinction of the stars, the temperature in the universe drops. Having originated in the fiery origins of the Big Bang, we sink into a cosmic winter, finding the universe gradually slipping into darkness. The era of starlight is over. The universe has become a cosmic graveyard. These are the last remnants of the stars that once illuminated the cosmos. They glow with a faint, ghostly light, a chilling reminder of the universe's fiery past. By 10 quadrillion years, these white dwarfs have become the dominant celestial bodies. This is the age of degeneration. It is a ghost universe that echoes memories of galaxies and stars that once shone brightly. The age of extinction is a vivid reminder of the endless cycle of birth and death in the universe. But even in its last gasp, the universe continues to evolve. Gravity, the sculptor of the universe, continues its work. Gravity, never resting, rips stars and planets from their orbits, hurling them into the cosmic void. These gravitational interactions sometimes lead to the birth of new stars, their creation heralded by ultra-bright supernovas, echoes of the past universe. Meanwhile, white dwarfs begin to disappear. Over trillions of years, they cool and shrink. Their light dims until they disappear altogether. Dying white dwarfs are reborn as black dwarfs. A black dwarf is the final evolutionary state of a star. Invisible to the eye, they mark the plunge of the universe into darkness. The era of black dwarfs begins. The universe, once a spectacle of light and color, is now a shadow of itself. The journey to the end of time continues in coldness and darkness. As time goes on, the universe continues its relentless expansion. Each region of space stretches and thins. Space-time itself is stretching. What was once an organized whole now expands endlessly into something like a multitude of distant islands lost in a boundless ocean. But within this void, a silent catastrophe occurs. Protons, the building blocks of matter and life, begin to decay. Protons, the heart of every atom, disintegrate into ghostly neutrinos and photons. Matter as we know it is disintegrating. The universe is slowly erasing the last vestiges of its physical history. All that remains are particles of light and black holes. At this point in the journey, the familiar physical phenomena end, plunging us into a new era of cosmic history. We are in the era of black holes. Even the seemingly eternal black dwarfs have disappeared, giving up their mass to the unrelenting pull of the expanding universe. The last remnants of stars have turned into cosmic dust. Black holes are becoming the main, if not the only, celestial objects dotting the universe. In an era dominated by black holes, the remnants of once-living galaxies, supermassive black holes, are of particular importance. Born from the deaths of massive stars and the merging of smaller black holes, these celestial titans have grown to incredible sizes, absorbing matter and energy on a scale beyond anything we could have imagined. These cosmic events emit gravitational waves, causing ripples in the fabric of space-time. We can think of them as the last sounds of the universe on the verge of its end, the slow ringing of a bell echoing through the vast cosmos. Such outstanding objects of the universe as black holes are not as eternal as one might think. In the late 1970s, physicist Stephen Hawking introduced the concept, now known as Hawking radiation, the process by which black holes lose energy and therefore mass over time. This phenomenon is a result of specific properties of quantum physics near the event horizon, where pairs of particles and antiparticles appear. One of the particles is sucked into the black hole, which helps the other to break their bond and escape into space. This leads to a net loss of energy, and hence the mass of the black hole. Over enormous timescales, this slow leak causes the black hole to lose mass and shrink. In this process, its once overwhelming gravitational pull slowly weakens. The result is the evaporation of a black hole. Such events mark the death of the last major objects in this universe, leaving behind a vast, seemingly endless cosmic void. Since the Big Bang, our universe has been expanding under the influence of a special force we call dark energy. Dark energy is believed to permeate all of space and act as the antithesis of gravity, causing the expansion of the universe to accelerate. At the same time, dark matter, which makes up 85% of the matter in the universe, creates gravitational attraction, acting as a counterbalance to this acceleration. Although dark energy seems to be the dominant force at present, we must consider the possibility of a shift in the balance of forces, and the journey through time continues. The heat death will eventually come. The heat death is not related to the transformation of our universe into hell through the evolution of stars. The scenario of the future fate of the universe is based on the second law of thermodynamics, according to which, in a closed system, entropy, or the state of disorder, increases over time. That is, the energy will dissipate in such a way that absolutely nothing will be able to form into something unified. You can think of it as heat energy leaving your cup of tea and dissipating in the room. Eventually, the temperature of the tea becomes the same as the room, so you can no longer get warm when you drink it. So, the drink is not doing its job. Galaxies will be too far apart, and stars will start to fade because there'll be no more necessary inflow of energy or matter for the evolution of stars, planets, or other space objects. The universe will become completely dark and empty. Dark energy may threaten not only heat, death in the future. If the expansion becomes many times faster over the next 100 million years, then the universe can expect absolute death. In this scenario, stars will not just stop forming. As in the previous scenario, nothing will exist, not even fundamental particles. Since matter, such as stars, remains unchanged and does not increase its mass through expansion, then, in a few billion years, the expansion can become immeasurably fast. The stars will not withstand such an influx of energy and will simply explode. Another scenario for the end of our existence is the Big Rip. It suggests that, since the acceleration of expansion probably cannot be influenced, in 200 billion years, it will become so fast that gravitational interaction will be broken. Planets will leave their orbits, and subsequently, the electromagnetic force that maintains the integrity of stars will not be able to resist dark energy. With even more time, even atoms will not be able to resist, and they'll be torn apart. Moreover, there's a possibility that after the Big Bang, everything in the universe will return to the first stages of the Big Bang. However, what will remain in the singularity will not look like the plasma that was at the beginning of the Big Bang itself. It will be cold and dilute, as opposed to hot and dense. That is, no matter how terrible the hypothetical end of the universe may be, there is a chance that this end will be a new beginning. Another danger to the entire universe may be hidden in ourselves. We all know that everything around us is made of atoms. There are two elementary particles in the nucleus of an atom, a proton and a neutron. We also know that these particles are stable within the nucleus, meaning they cannot decay. But what if this is not necessarily true? The proton is one of the most common particles in the universe. It can exist even outside the nucleus. The proton has reasons to be stable, namely the laws of conservation, of energy, charge, and baryon number. Although, according to the standard model of physics, the proton cannot decay in any way. The latest theories, such as the theory of grand unification, which combines the three fundamental forces, electromagnetism, weak and strong interactions into one, allow it. In the distant future, there's a possibility that this particle will decay. This seemingly unlikely process is unlikely to cause disaster to the entire universe. But if it happens on a massive scale, then, in millions or even billions of years, part of the universe will cease to exist. The proton decay will destabilize the nucleus of atoms and produce decay products that can affect the entire structure of the universe as matter begins to decay. But the whole world will not disappear. The entire system of galactic evolution in the regions where proton decay occurred would be disrupted. The people of the future can exhale. The protons in their bodies are likely to decay. But the 100 million year time frame may bring another threat in addition to heat death and the Big Bang. If the collapse of protons is too large and strong, it will trigger an inevitable scenario of the terrible end of the universe. But not because of protons alone. The destruction of all matter in the universe, without even a hint of its former existence, is hypothetically possible through a bubble. You've probably heard of the Higgs boson, which is a fundamental component of the Higgs field, a theoretical field that permeates the entire universe and to which particles gain mass when they interact with it. In addition, the Higgs field can affect the vacuum. We are used to thinking that a vacuum is empty space, but there are quantum fields in it, so a vacuum simply contains as little energy as possible. The field determines whether the universe is in a true vacuum or a false vacuum. A true vacuum means the universe is stable and has the lowest possible vacuum energy state. A false vacuum, on the other hand, means the universe is metastable, meaning it has higher energy but less stability. According to modern theoretical data, our universe is metastable. This is precisely the threat to all future life and matter. If, in 100 million years, an event occurs in the universe that would have enormous energy, such as a massive proton decay, then a small particle of the universe will hypothetically be able to enter a state of true vacuum. Thus, a bubble of true vacuum will form, which would expand at the speed of light, destroying all matter and fundamental particles in its path. Life can hardly appear in any form after such an intervention. The universe as we know it will change over time and one day become completely unknown to us. It will continue to evolve, but like all of us, it will begin to fade away at some point. We don't know when this will happen. No matter how hard we try to look into the future, we'll never get an accurate prediction. One thing we can say for sure about the future is that humanity will see more than one outstanding discovery, which perhaps in 100 million years will reveal the full history of the universe and ourselves to the humanity of the future. These voids exist on cosmic time scales, but their implications extend even further. The study of these voids can provide important information that helps refine our current cosmological models and theories. For example, the size and distribution of cosmic voids can serve as a unique test of cosmological models. If a model can accurately predict the properties of these voids, it confirms its accuracy. Conversely, any discrepancies between model predictions and observations may signal the need to refine or even develop a new theory of physics. In fact, these great cosmic voids, once thought of as mere empty spaces, have taken a crucial place in our quest to understand the universe. But what if these voids are more than just empty space? Their study has spawned theories that extend beyond our familiar universe, bordering on the realms of the speculative and the extraordinary. One such theory includes the concept of alternate universes or the multiverse. The idea that our universe may not be the only one, but rather one of many universes existing in parallel to each other. According to some theorists, these great empties could potentially be more than just vast spaces of nothingness. They could, in fact, serve as interfaces or gateways to these alternative universes. This assumption is rooted in certain interpretations of quantum mechanics and string theory, which postulate the existence of other dimensions beyond the three spatial dimensions and one temporal dimension that we currently perceive. If these extra dimensions exist, they could potentially contain many alternative universes, each with its own set of physical laws and properties. In this context, the great empties may be areas where our familiar four-dimensional universe thins and gives way to these other dimensions. However, it is important to note that this idea is highly speculative. While it offers an intriguing perspective and has inspired countless science fiction stories, it remains far from being accepted by the mainstream scientific community. To date, we have no concrete evidence for the existence of alternate universes or other dimensions. Moving on, we encounter another fascinating idea, one that unites the immensity of the universe with the infinitesimal quantum world. This concept revolves around quantum fluctuations. In a quantum sphere, particles and energy constantly appear and disappear, creating a frothy sea of fluctuations. But what do these microscopic phenomena have to do with giant cosmic voids? The answer lies in the earliest stages of the universe's development, shortly after the Big Bang. During this period, the universe was extremely small and hot, and in such a state, quantum effects could have had a significant impact on a cosmic scale. Quantum fluctuations occurring at this time may have intensified as the universe expanded. These amplified quantum fluctuations could have led to an uneven distribution of matter and energy, causing regions of lower density to evolve over billions of years into the vast cosmic voids we see today. In this scenario, the great voids are like ancient imprints engraved on the fabric of the universe by quantum fluctuations in the earliest moments of its existence. However, while this theory is intriguing and has some basis in our current understanding of physics, it still remains a hypothesis. Verifying such a theory is a difficult task that requires accurate measurements of the large-scale structure of the universe, as well as a deeper understanding of quantum physics and cosmology. Nevertheless, the prospect of connecting the quantum realm with the cosmic, the smallest scale with the largest, is an enticing one. Another fascinating hypothesis plunges us into the complex and abstract world of topology, the mathematical study of space and its properties. In the context of the universe, topological anomalies or space defects refer to irregularities in the fabric of space-time. Just like defects in a fabric, these anomalies may represent areas where the normal structure of space-time is disturbed. But where could these anomalies have come from? To answer this, we must go back to the inflationary period of the universe, a fraction of a second after the Big Bang. During this ultra-fast expansion phase, the universe grew exponentially. Although inflation smoothed out the overall distribution of matter and energy, it may have also exaggerated tiny irregularities in the fabric of space-time, causing topological defects. These defects could have acted as barriers around which matter could not easily accumulate, eventually leading to the vast empty spaces we now know as cosmic voids. The study of cosmic voids would not be complete without examining one of the most mysterious objects in the universe: black holes. Specifically, we are referring to primordial black holes. Unlike the black holes we are familiar with, which form from the collapse of massive stars, primordial black holes are assumed to have formed shortly after the Big Bang, created by extreme density fluctuations in the early universe. But what do these ancient black holes have to do with cosmic voids? One claim suggests that these voids may be teeming with primordial black holes. According to this idea, the large voids may be the result of a high concentration of these black holes hidden within these regions. Since they do not emit significant radiation, they would be difficult to detect directly. However, their presence could have a gravitational effect, actively clearing their surroundings and contributing to the enormous voids we observe in the cosmic world. Another theory intertwines the emergence of the great voids with the elusive nature of dark matter. Though undetectable by conventional means, dark matter is thought to make up about 85% of the universe's matter. It plays a crucial role in the formation of cosmic structures, weaving a vast, entangled network that links galaxies together. These strands of dark matter, known as filaments, serve as scaffolding for the universe, guiding the formation of galaxies and galaxy clusters. But what if something were to break these threads? What if a massive event or unknown force caused these filaments to collapse or disintegrate? This is where cosmic voids come into play. According to this theory, the collapse of strands of dark matter could lead to the formation of these enormous voids. The disappearance of these filaments would disrupt the flow of matter, leaving behind vast empty expanses. As we now understand, these vast expanses of emptiness are far from barren wastelands. They are treasure troves of clues and mysteries about the universe and its composition. From the formation of large-scale cosmic structures to the behavior of dark matter and dark energy, the mystery of the great voids forces us to rethink our understanding of the cosmos. While we may not yet have all the answers, and remember, every time you look up into the night sky, you see not only stars and galaxies, but also the invisible cosmic voids. These silent guardians of the cosmos continue their eternal vigil, keeping the secrets of the universe hidden within their vast expanse. But what if these cosmic entities are not the end, but rather the beginning? Some physicists speculate that singularities inside black holes could give rise to new expanding universes. Thus, our universe could be the inner part of a black hole belonging to another parent universe. In this model, the Big Bang would correspond to the formation of a black hole singularity in the parent universe, and the expansion of our universe corresponds to the internal growth of the black hole. So, what was there before the Big Bang? It could be the inside, of a black hole in another universe. And maybe every black hole in our universe can give birth to a new universe inside itself. Of course, this idea, like all those we've discussed, is a hypothesis and not without problems. How can we test this theory? Can we observe the effects of the parent universe, and how do we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework aimed at reconciling the two giants of 20th century physics: quantum mechanics, which describes the very small, and general relativity, which describes the very large. Loop quantum gravity implies that space itself is not continuous but consists of tiny, discrete loops. It consists of tiny, indivisible loops, just as a piece of fabric consists of interwoven threads. Applied to cosmology, loop quantum gravity, or more exactly, loop quantum cosmology, offers a rebound scenario similar to the Big Bounce, which we discussed earlier. In fact, loop quantum cosmology provides a specific quantum mechanical description of the universe's evolution, including the Big Bounce scenario. Instead of collapsing into a singularity, as required by traditional Big Bang theory and general relativity, the universe shrinks to a minimum size. But quantum gravitational effects become significant and counteract the contraction. Then, the universe bounces back and begins to expand again. This means that our universe may have undergone a series of expansions and contractions, each of which began with a quantum jump. So, what was there before the Big Bang? From the point of view of loop quantum cosmology, it may be another phase of the universe, the contraction phase, which preceded the quantum jump. In loop quantum cosmology, the idea of a quantum bridge is truly fascinating. This bridge represents a transitional phase connecting our universe with its predecessor. Instead of a singularity, the universe undergoes a quantum leap and starts expanding. This jump, this transformation from contraction to expansion, can be seen as a quantum bridge from the old universe to the new one. This quantum bridge is not a physical bridge in the conventional sense, but a phase of the evolution of the universe controlled by quantum gravity. So what is beyond the Big Bang? According to loop quantum cosmology, the previous universe is connected to ours by a quantum bridge. Although this theory eliminates the singularity at the Big Bang and offers an elegant quantum description of the evolution of the universe, it still faces considerable difficulties.